AI often drafts perfectly formatted emails or solves complex problems in seconds. These outputs are generated by a computer program running a massive statistical pattern matching operation. We built these programs using a technique called machine learning. Instead of manually writing rules for every possible scenario, developers feed the program vast amounts of raw data so it can discover the underlying patterns independently. This animated diagram shows a sorting funnel processing raw data. We start by dropping in thousands of labeled images of horses and zebras. We don't give the program a biological definition of what a zebra is. It has to process the sheer volume of images and derive those characteristics by itself. As it chews through the data, a structural network builds inside the program. It isolates that recurring pattern as the mathematical signature of a zebra. Once trained, the true test happens. A new, unseen photo drops out of the funnel. The model scans the new image, recognizes the mathematical signature of the stripes, and correctly applies the tag. This moment of successfully categorizing entirely new data is called inference. Because this process relies entirely on the information it was trained on, the outputs you get are highly calculated predictions based on past patterns. This is the mechanical reality of the model, rather than a conscious understanding of your request. We steer these predictive models using dynamic training methods, like reinforcement learning. Instead of just static analysis, the model continuously refines its behavior through a process of trial and error. This video timeline tracks a predictive model targeting different animals in motion. The model makes a guess. Guessing incorrectly flashes a red penalty, but when it selects a zebra, it earns a green reward. Over thousands of attempts, the model adjusts its predictive strategy to maximize that total reward. When you use an AI app, your typed instructions act as a real-time steering mechanism. The specific words you choose trigger the model's predictive pathways, guiding it toward the result you want. But this mechanical reliance on past data creates a serious vulnerability: data bias. If a food distributor trains an AI exclusively on thousands of images of red apples, the system will fail to recognize a green apple, no matter how perfectly you prompt it. This animated diagram illustrates what happens when a broad prompt meets skewed data. The text prompt asks to generate an image of a professional office. The screen instantly populates with identical glass skyscrapers. Because historical business data heavily overrepresents urban hubs, the broad request triggers the model to output a monolithic stereotype. These outputs reflect the historical or incomplete nature of the training data. The user must actively anticipate these mechanical gaps to ensure the final result remains fair. This text editing interface demonstrates a precise four-step framework to bypass systemic bias. Specify your exact output, define your target audience, provide fair references, and use follow-up corrections. The initial vague sentence is systematically expanded into a structured prompt detailing audience and context. Let's apply this to a practical test. If we simply ask an AI to generate a typical adult learner profile, the model defaults to its most common predictive pattern, a 22-year-old business student. You need to override this default. Take a moment to think about how you would apply the four-step framework to rewrite this prompt and actively correct the demographic stereotype. The solution requires strict constraints. As the timer reaches 0, the prompt morphs into a highly specific set of instructions. By explicitly instructing the model to profile a 35-year-old healthcare student balancing a part-time job and family, we force the AI out of its predictive rut. Effective prompting requires aggressively constraining the model's predictive variables. Precise instructions force the system to bypass its default patterns and deliver an accurate, unbiased result. Beyond bias, the data powering these models has a hard temporal boundary called a knowledge cutoff. This cutoff marks the exact date the model's core training ended. The program lacks internal knowledge of events, news, or scientific discoveries that occurred after that point. This workflow diagram tasks. These explicit date modifiers direct the model to pull current context from external calendar and email tools, successfully bypassing its internal cutoff. Even with these tools, you must separate what the model inherently knows from what it generates in the moment. Always cross-reference time-sensitive statistics and breaking news with external authoritative sources. AI mastery comes down to recognizing what the technology actually is. It is a powerful engine of pattern recognition. To function responsibly, it demands precise human context, requires relentless iteration, and your critical oversight.